So we know that there's a relationship between displacement, velocity, and acceleration. And essentially the relationship between displacement and velocity is that the displacement is, the velocity is the ratio of the change in position or change in displacement over the change in time. In other words, the velocity is the rate of change of the position graph or the slope of the position graph. So we know that we were looking at the rate of change, or the rate of change of a quadratic function happens to be linear. The rate of change of a cubic function happens to be quadratic. And we're going to see if we can use this kind of relationship and to help us analyze displacement, velocity, and acceleration. So when we look at these graphs here, so the example 1 here, we've been given a displacement graph. Okay, so along the y-axis you have displacement, along the x-axis you have time, and we want to know the velocity. And the velocity is the rate of change of displacement over time, or the slope of this graph. So if I want to find the velocity of this graph, what I can do is just calculate the slope. So I'm just going to choose 2 points here. So I'll go from here, do a little slope triangle to here. Okay, and you can do it anywhere you want. And when I look at the slope of this graph, I know this is a rise of plus 10, okay, over 25 seconds. This is in meters. Okay, so we know that the rate of change, or the slope of this graph, is going to be 10 meters for 25 seconds. And we can simplify this into, this will be 0.4 meters per second. Okay, so that's fairly straightforward. For a linear function, okay, we know that the slope is constant. Okay, so we went from a degree 1 linear function to degree 0 constant value. We can do the same thing with this next graph. However, there's a little bit problem here in that if we want to find the rate of change or the slope of this graph, the slope seems to be changing. Okay? So we have this quadratic, essentially this curve is quadratic, and we know that the rate of change is not a constant function like we have here. We have constant slope. The slope, in fact, is changing, and it's changing in a pattern. And what we can do is we can predict that the rate of change, or the slope function, the value of the slope, is changing in a linear pattern. So how do we go about doing this? Well, we can do what we did before. We can just take the average slope between 2 points and see if we can come up with a function. And we know that the function is probably going to be a linear function. Okay, so what I'm going to do here is I'm going to find the slope between these 2 points. Okay, and that slope segment, I need a little bit sharper pen, I think, to do this. Okay, so my slope segment here, in the first second, it looks like we've gone 5 meters. Okay, so this is going to be 5 meters. 5 meters per second. Okay, this next section here, it looks like we've gone 15 meters per second. This next section here, looks like we are increasing 1, 2, 3, 4. It looks like it's gone to 25 meters per second. Okay, and you can probably see what the pattern is, that looks like the velocity is changing in a linear pattern. So it looks like we're going up by 10 meters per second. So I'm going to predict that this next slope segment is going to be 35 meters per second. So if there's 1 second there, go 1, 2, 3, 4, 5, 6, 7. Yeah, it's 35 meters in that 1 second. Okay, and we can come up with the slope, a slope function for that. So this is the idea then, is that knowing that the rate of change of a quadratic is linear, rate of change of a cubic is quadratic, rate of change of a linear function is constant, okay, we can maybe analyze how we get these different velocities, and we can maybe predict a function for these velocities. So we're not gonna, since this is changing, we can't really say the rate of change is a constant function, but we could say it is a function itself. And so maybe we'll just do a little quick table here and maybe see if we can come up with a function. So we're just going to say time velocity, and we'll use the average time here. We'll just use 0.5, 1.5, 2.5, 3.5, and 4.5, and see if we can come up with a function here. 15, 25, 35, etc. Okay, so if we look at the change of the time and the velocity, we could probably come up with a fairly simple calculation. So if I multiply the time by 10, it looks like I get the velocity. So my rate of change, or my velocity function, is equal to 10 times the time. Okay, and this is, this is not a simple thing to do. I've kind of done it quickly because I know I've seen this before and I know what I'm doing, but there's this analysis that we can actually come up with a function that finds the velocity of these graphs based on a displacement graph.